Hi, everyone. Thanks so much for joining us today for Flow Simulation, a part of our What's New in Solid Edge ST10 webinar series. My name is Diana Dietrich. I'm the Marketing Director here at Swoosh Technologies, and I will be hosting today's session. So we are Swoosh Technologies. For those who aren't too familiar with us, we're an award-winning leading provider and partner of Siemens PLM, and we're also partnered with several leaders in the industry, including Mentor Graphics, Markforged, CamWorks, Map3D, and Keyshot. We're dedicated in helping you meet your goals with the best software solutions, technical support, and process-based training out there. Presenting today is Application Engineer Dylan Malek. Dylan is a certified Solid Edge professional at Swoosh and is one of our most sought-after Solid Edge training instructors with a great working knowledge of best practices in the program tool. He's seen the growth and changes of CAD, of various CAD systems, and has hands-on experience in sheet metal fabrication, structural design, surfacing, rendering, animation, 2D drafting, and 3D modeling, just to name a few. In today's session, we're covering FloEFD. What is FloEFD exactly? It's a fully embedded computational fluid dynamics software solution for CAD that gives insight on heat transfer analysis and fluid flow design challenges. With FloEFD, you can determine the impact of a liquid or gas on product performance during the design phase. Combined with Solid Edge, it provides great insight on the impact of gas or fluid flow, which allows you to address problems earlier, reduce costly prototypes, and eliminate rework. So I was going to be showing how leveraging flow simulation in Solid Edge is a valuable asset for your team with a presentation, followed by a demonstration on working within FloEFD. So if you have any questions, please feel free to add these into the questions box located in your GoToWebinar panel. I'll submit your questions anonymously to Dylan during our Q&A portion, so please don't be shy, ask away. So all right, I'm going to go ahead and send this on over to Dylan, and he will take it away.
Thank you, Diana. All right, so as Diana mentioned, what the actual definition of what we're referring to as FloEFD. Again, as fully embedded, we are talking, it's another tab inside of Solid Edge, and it kind of just walks you through, which I will explain pretty in depth on the steps that it's going to take to kind of create a study. The EFD stands for the engineering fluid dynamic part of the name. So again, there is a really simple setup for the basic steps to create a computational flow without having to know all the math in the world to do it. All right, so some of the key features of it, again, the short learning curve. Very few steps to get through a study, which you'll see me run here shortly from the beginning to end. Again, Solid Edge CAD data. Again, we bring in any kind of data external. At that point, it's a Solid Edge file. You can run your computational fluid on that. All right, let's switch over here. So who are the people looking at this? You know, we have a lot of customers in the bottom segment here in the automotive, the household and process and manufacturing for Solid Edge. We do have a lot of customers using NX for the automobile, aerospace, in the higher end industries. And again, this is a perfect fit for all those. It's a crossover. It's kind of a general tool for all these specific industries. All right, so let me switch over to Solid Edge. Kind of give you a breakdown of what we're looking at here. So we just have an amplifier. Trying to cover all so you can kind of see what we're working with on the inside. Pardon me. We have some heat sinks, and of course we have all our electronic components. We got our printed circuit board with transistors and some capacitors mounted to it. Again, all electronic equipment creates heat. So that's kind of what we're going to be looking at on this particular study, is looking at the heat on these transistors, the heat of the board itself, and let's just start the study. So like I said, it's just another tab inside of Solid Edge called Flow Analysis. I also like to kind of use the sidebar because I kind of had that set up with some of the basic tools I'm going to use for this particular demo. So just to start you with, the wizard. That's where, you know, the guys I learned this from said you're going to probably start 90+% of the time. So we'll just walk through the wizard. Got some predefined things that you just have to define, but make it a lot easier as you go through the rest of the study. Give it a name. and I'll just walk through what these kind of do. We're looking at our type of template units that we're going to be working with. Of course, when you start solid edge, you tell it it's going to be isometric or anti-inch. So same kind of simple thing we have here. We have one for US, and I have one that I already set up for my study. Just go through and change a few things. As you can see the list. Specifically, I know the motor we're going to be dealing with. I know the RPMs. So this originally was set to be in radians per second. So didn't have that listing, but if you don't happen to know that, you can always just type in 1000 RPM. It'll convert it. Or you can just change the value anytime you want. So let me put that back to RPM. All right, in this study, we're going to be looking at the inside of this cavity here. So that's the setting we want. Obviously, we have external settings too, where it creates a bounding box outside the geometry to test for flow conditions. We're going to leave this exclude, which I will explain what that does in a second. And we want to do heat conduction on the solids. All right, so what type of material is this going to be sitting in? So under gases here, we're just going to say regular old air. All right, look at some of the other predefined lists. It's got an extensive list of liquids and gases and some fun ones, which I haven't found a use for, but I would like to see what applesauce kind of flow does. So anyway, that's all we need to set for air. And what we need to look for here is basically the box that it's sitting in, which is in itself a big heat sink, and it's aluminum. So we're just going to go through and say this big chunk of material, we're just going to make that aluminum. And what type of condition is it going to be transferring? So it's not adiabatic, so there is some transfer. So we're going to say, as I was told, there's a 5 watts per meter per second. And we're going to go with 25 degrees Celsius for all the temperatures that we're going to set. Exterior, interior, starting temperature. So that's the next few things we're going to go through. Again, we'll just set the, and of course the solids, which would be the materials you see here. Starting temp initial at 25. And there we have it. All right, so as I mentioned earlier, we have our computational domain. So it builds a little bounding box, and that first setting that I told to ignore things, that would be the area outside of it. It's going to ignore, and you can see these little arrows. That allows you to just quickly just kind of drag and adjust to the size of a bounding box that you want to work within or build around. And this one was good, so we don't need to see it. All right, so let's go through and talk about what we see here. A lot of this matches across the top, like it always typically does in solid edge. But we have all our data, and if I just right click and say custom tree, so this is where I'm getting the information from. So these are all the different things you can solve for: LEDs, different heat pipes, different types of material simulations, fluid subdomains, which I don't really need because I don't have a secondary fluid. It's just air. So I can just turn that off. When I go back, it removes it from the list. Simple as that. So if I'm doing these type of studies, this is really all I got to work with. So let's go ahead and start adding some information to it. So we have to define our solids that we're going to work with. We can pick them from the Pathfinder. We can pick them from the screen. Either way, whatever is easiest for you. And you can see we have a list, some user defined. Of course, we do have, again, an extensive list of predefined materials. This is an 8-layer PCB board. There's one thing I extra got to do. Notice this arrow that pops up. I have to define the thickness orientation. So the board is obviously in that thickness orientation. So we'll just define that. And these transistors, again, are another piece of the puzzle we want to solve for. So we're going to look at some temperatures for these guys. So we're going to pick those first and say insert those. And these are going to be thin, small outside package transistors. All right, there we go. boundary conditions. That's next in the list. And all this is being activated by just clicking on it, right click, insert a boundary condition. All right, so this is going to talk about where the airflow is going in and out of this object. All right, we can look down here. We have the fan on the other side, and of course we have the outlet vent on this side. The outlet vent itself is a part, so that's just one of the things you have to do to get ready for studies. You're going to just have to create some extra geometry at some time. You can't pick an empty space to tell a boundary layer. So we're just going to say that is what we're looking for, and what type of pressure opening is it. We're just going to say an environmental, which is basically, again, looking at the temperatures we set previously, so we don't have to fill that out. It's going to be pointing in and out, basically dictating we have the ability for air to flow in and out of these vents. So obviously, depending on where the higher temperature is, typically higher energy to lower energy, so you're going to have air flowing out in this scenario. All right, especially if we have a fan, which is kind of next up in the list, blowing cooler outside temperature air in. All right, so we're just going to insert a fan. So you can kind of see how easy this really is. Specifically, you want to make sure you want to pick a piece of geometry here, not the entire thing. We're looking where actually the fan blades would be, so it would be that kind of outside ring. And again, we want to predefine what type of fan, or have a fan for the predefined list. There we go. And of course, this is a rotational type motor. So the first setting defaults to is the normal to face, which is more like a squirrel cage blower motor. This one actually swirls. So this is kind of where that 1000 RPM comes into play. And that's it for the fan setting. And there we go, have our arrows blowing in. All right, so now let's define a couple heat sources here. We're just going to do a couple. Sure, grab the right one. So the first one, we can just either grab it from the list here, which would be the PCB board. We know, when this thing has some electricity running through it, it's going to put out 220 watts of energy, so it's going to be heat dissipated from that. And again, let's add from these guys. So the transistors themselves are 5 watts, so we're just going to say cumulative 20 across that little heat sink. That looks pretty good. Let's go ahead, because you notice up here it tells me what they are, but down here it just kind of gives you a vague name. So I'm just going to go rename this PCB and do the same thing for the transistors here. Simple as that. Just makes it a little easier to see once I run some reports. The names will make a little more sense. All right. So we have all our parts defined that we want to work with. So now we have to define the goals that we want to achieve. So again, just a simple enough, clicking on that, insert a volume goal. So what we wanted to do is look at some temperatures. And again, we want to look at those, and we want to find solid temperature. Can't see that up there, but let me spread this out for you. So these little bars are looking at minimum, average, and a max. So I was kind of worried about the average and the maximum temperature of these transistors. And last thing is insert another goal, and we want to look at that fan, and we want to look at the actual volume flow rate, how much air is going to be pushed through there, and what volume it is. All right, so we got our goals. Last thing, typically like we do anytime in Solid Edge, like a simulation, last thing you do is mesh the object. So I'm just going to do a global mesh, have this little menu bar that pops up. You go to the manual, just like our other simulation, you have a lot of settings you can define. I'm not an expert in this, so I kind of take the automatic setting, kind of keep it low at first, and hopefully it works. And once it gets refined, I can bump it up to a higher setting. So let's go ahead and accept that. Last thing to do is run it. All right, I want to change some settings here. This is kind of cool. You can actually move it. So if you have another computer on the network, you can use its resources to let it do the study. I'm just going to leave it on this computer. You can actually close Solid Edge. So if you don't want to tie up a Solid Edge license, so that will go back in the pool while it'll do its calculation. And of course, we want to still be able to do some things. So I'm just going to set it to run 6 cores on my CPU while I'm still doing this webinar and running Solid Edge. So it's not taking all my resources. Then it just hit run. It just takes a second to get started. But once it does, I'll go ahead and switch over and actually show you case 1, which is completely defined. So as you can see, it starts popping up in this little geometry preparation tool. Once this is running, there you go. Let me switch back over to Solid Edge momentarily. There we go. All right, so I'm just going to go ahead and toggle over to case 1 while that's doing its thing in the background. And case 1 is pretty much the identical setup that we have initially. I'm just going to go ahead and run the results, which are already been created. So I'm just going to load those. This, again, only takes a second. So you can see, again, another benefit is the ability to run multiple scenarios quickly based off the same CAD geometry, just making a few configurations. All right, so that's loaded. So let's take a look at some of the information that we got from it. And of course, this is the velocity one that we set up for the fan volume. And so again, this is not temperature, this is actually velocity. So there's the fan coming in. You can kind of see the airflow going around. Oops. Kind of missing going on opposite side of that heat sink and kind of going around in the middle of the board. So again, that was the second thing we were kind of concerned about. Some temperatures here. Turn on the PCB board temperature. You can hide that. See it underneath here. So we're looking at 90 degrees plus, probably in some areas. There's some tools that I like to turn on. Let's look under display. Let's turn on the global min-max. So that kind of gives me some key points. So the center of the board, obviously, there is the hottest. Let me turn off this case and look for the minimum. So here we have the least amount of airflow right there, kind of a dead spot above the vent. Turn that back on. Let's take a look at what that actual temperature is. And we're looking 90, 91, and kind of the mid-range, and somewhere here on the outside edge where we get a lot of airflow. So we got a variation from 64 up to 91 based on the current setting. All right, so something we can also do is look at if that changes. So I can just turn all this back on, the velocity plot. You know, so there's a little arrow here, so we can actually move this. So I can set one up for temperature. This one, again, is set for the volume of air. So I can actually move this through there, and it's going to show different plots based on location of where that airflow is located just by dragging that. All right. So let's take a look at the reason why we're not getting that flow. So let me just turn the probes off. We'll leave that temperature on, and we're going to create the cool part of this, which is, you know, the flow trajectory, which is showing the actual airflow through this. So we're looking for a starting point. Again, that's going to be the fan. Let's just say 50. Say flat arrows, make them 5 millimeters long, and we want to go with velocity again, and let's generate that. So again, it's really quick to create. There we go. So you can see the 3D arrow look here displaying, and again, this was a fan, so you can see the twisting of it. So let's actually animate that. So it gives a lovely representation of the airflow and the reason why we're getting some really high temperatures in the middle. All right, so that was case study 1. All right, let's switch over to case study 2. Let me just go ahead and pause that. And again, loads up, take a second to load its result. All right, so what we have here is, I should have kind of brought this up so you can see the difference. But what did happen is the fan moved over about 4 or 5 millimeters in this configuration, and a much larger heat sink was added to the PCB board. All right, so let me just turn on PCB temp. All right, and again, let me get that out of the way so you can see that before, where it was predominantly red throughout the entire circuit board, now it's a lot lower in temperature, even in the hottest areas. If I pull a probe off, it's 84. So previously it was relatively 90 or close to that. So that is the hottest part, which is a very small portion of it now. All right, so let me again show you the flow. And there we have it again. So with that heat sink in the middle and the fan moved over, we get a lot more airflow split around there. And now if you want to compare the two, we have, look at the results, we can compare some objects here. We can tell it, let's look at case 1 and case 2. Let's look at PCB temp and the flow trajectories. All right, PCB temp. It'll bring up, so if I can, loads up here, I can, there it goes. Make that a little bit bigger so you can vastly see the greater cooling capacity just by moving that fan over a little bit bigger heat sink. You want to grab that snapshot. Obviously, you could use these for whatever purpose, email illustrations. Let's look at the next thing, which was the flow trajectory. I guess I didn't grab a shot of the first one in case, but here's the second one, the flow study. And what's still going on behind the scene, let's go back here, and still not done with the calculation, but currently no warnings. And typically they'll go through. We're going pretty slow right now, probably because I'm doing a go-to meeting and running a simulation at the same time. So this study is not done, so it would actually be finished, and I have all my plots once it's done. All right, so that is what we have for our flow simulation example today. Diana, back to you. Any questions?
Okay, so we do have a few questions in our queue today, but I just wanted to remind everyone that if we don't get to your question today, I'll get your questions over to Dylan for an answer. So please, if you have any questions that do arise during the remainder of this session, add them into the questions box. All questions will be asked anonymously during this portion, so don't be shy and submit. So Dylan, the first question that we have in our queue is, do I have to have FloEFD in order to use flow analysis, or is this something built into Solid Edge?
It is an add-on to Solid Edge license. It is part of Solid Edge, so it's a separate install. But unlike Keyshot, where it takes you out to a third party kind of view, interface you have to learn. This pretty much just stays in Solid Edge. Results are exported out of Solid Edge, and the tools kind of work left to right. You know, the toolbar, pretty much everything is Solid Edge. So that's how you're going to probably see it. So it's really integrated part of the tool, but you will need a separate license to make it work inside of Solid Edge.
Another question that we have in our queue is, would I be able to make real-time changes, or do I need to do something special in Solid Edge to edit?
No, it's again, just get out of flow analysis. You can leave your studies as they were. I guess it would the best thing to do, because this one actually has configuration. So we have 3 different types of configurations for it. All you have to do is create a new configuration, and if you wanted to go into the part file itself, you just double click it, takes you to the location where the part was made. If you want to change the size of the fan, if you want to put a bigger, test a larger fan, just create another fan inlet, make another configuration, bring it back into simulation, and just run the new iteration with the larger fan diameter, and that's it. So it's really simple to get back and forth and not have to import, export data to make it work. It updates automatically. You just go back and ready to run the next simulation.
Okay, another question that we have in our queue is, we do a lot with pressure drop through an assembly based on pressure flow. Is this just a different goal set?
Yeah, absolutely. No, that is absolutely what it is. It's just a matter of going through and adding that as a basically a goal, and of course, what type of information that you want to just glean from the list right here of components that you're going to be working with. That's really much all there is difference between one setup to the next setup, because it does obviously more than just what I showed you. There's an LED kind of scenario, and there's thermal. Again, some Solid Edge to say we do have some thermal tools built inside of our simulation. These are, for example, if I want to see if this heat sink gets a certain amount of heat from these, and is that going to transfer that heat to another part? So we do have radiation, convection, heat generation, and flux built into our simulation, our advanced simulation that's part of our assembly. But as for the airflow of showing the volumetric flow of air through this product, that's where it stops. That's where we flip over to flow analysis, and that's where these guys do both and actually show, what I showed you a while ago with the study with the little trails of arrows showing actually how it's going to flow through the product. Again, externally for validation, flow around parts for airflow studies. So there's multiple ways this can be used.
So we have a few more questions from the queue. So another question we have is, in the wizard panel where it shows the initial conditions, is this a predicted number, or are these numbers predefined?
Those are predefined values. You can always go back into these settings to change them to your own values. For example, I can go back into units anytime. Mine was set to my custom one, but I can go through and change any of the values that I set previously just right here for this particular study. Again, you can go change as you create the wizard. You can actually create new. You can create your own settings just by creating your own, create new, and create your own modified list. Just call it your name, my settings, and go through and adjust all these, and that's it. One-time setting, and the next time you do your study, all those are predefined, so you don't have to worry about setting those. Just go pick it from the list. A couple studies, all your settings will be done. You never really have to worry about going back.
Okay, so this question is referring to the assembly based on pressure flow. So one must create a separate part for each outlet, inlet, opening, or can we just use existing part geometry?
You could, depending on the complexity of that part geometry. Anybody who knows CAD, drawing helical profiles is probably one of the most processor intensive things. So trying to represent that here that's why I just kind of have a disk representing the fan. Objects like the box itself, it's got a pretty feature rich part, a lot of geometry here, but it's a simple geometry to work with. So it really comes down to the complexity, not so much the size. That's what you would. And again, when you're thinking about finite element analysis simulations, you always want to simplify the models. You don't need to have the radiuses and a lot of complex features to actually get an accurate study. It's just going to increase the speed of the study. So, you know, if you have a really great computer, have at it, you know, keep the geometry as is. I'm working off a laptop and not as much power, so keeping it simple is kind of where I need to keep it.
Okay. So this question is about the flow analysis tab in general. Is this something that's built into Solid Edge, or do I have to have FloEFD in order to use flow analysis?
You won't see this tab at the top. If you have it, you may see a flow analysis Pathfinder tab, but it'll just be blank without anything. Kind of same thing you can, like on our standard parts, you can start standard parts, but it'll probably bring an error up. So it, again, is part of Solid Edge, but the license was going to activate it, and then once you load it, you're going to have this menu bar as part of the install. So that license is required specific for it.
And then we have time for one final question. This is about the licensing. Do we have to pay for a license for FloEFD, or is this part of the Solid Edge licensing we currently have?
It's a separate license. I don't think it's part of the premium package, kind of like the simulation is. I still think it is considered an add-on package. So there would be a different pricing for that. You can, I don't know what that is. You need to contact somebody, Diana, or else we can get you a pricing on that if required.
All right. Thanks so much, Dylan. I'm going to go ahead and switch this on over to me real quick, and then we're going to go ahead and end it. Thanks so much, guys. Before we head out for the day, I just want to invite everyone to our final session in What's New in Solid Edge ST10 webinar series, Technical Publications. Dylan's going to be covering how Solid Edge illustrations and 3D publishing, a part of that Technical Publications family, can help your team easily create illustrations from Solid Edge geometry and PMI annotations, while also generating customizable multi-page documents. So the final session is set for Wednesday, March 14th at 2 p.m. Central Time. So please feel free to register for the webinar. It's free. The link is listed on the screen. This is also going to ensure that you receive the replay post-session. So be sure to sign up in order to get on the list to be one of the folks to receive that webinar replay. Speaking of replays, please be on the lookout for the flow simulation replay email that will be hitting your inbox in the next few days. There will also be a link in there to register for the TechPub webinar for those interested. All right, thanks for joining us today. If you guys do have any questions post-session, please don't hesitate to reach out to us by phone or by email. Or if you're already working with the Swish rep here, please feel free to reach out to them as well. Either way, we're all here to help you develop custom solutions that are designed to tackle your company's everyday challenges. So hope to see you for our next session in March. Thanks, Dylan. Thanks, everyone. Bye.